So this is a tutorial introducing electrical circuits and the ideas of current, voltage and resistance. Remember to use the pause button. There's quite a lot of big ideas in here, so pause and re-watch sections if you need to, and bring all your questions to the lesson. We're hoping that by the end of this you can understand the concepts of voltage, current and resistance. You can understand how current and voltage vary in series and parallel circuits, and that you can know and use the symbols and equations confidently that we're going to be using when we look at electrical circuits. So one thing that can make electrical circuits difficult to understand is that we can't see what's going on inside them, because all the things that are moving are really tiny. So it can be helpful to have a model in our mind when we're thinking about the circuits. Now, one model that some people find useful could be this Cole model of an electrical circuit, but there are lots of different models, and obviously models show different aspects of a circuit successfully and less successfully. So this model is good at showing some things, but it's not so good at showing other things. So one thing that you can do is you can try and come up with your own model, or look at other models that people have put forward to understand a circuit and compare them and contrast them and evaluate which one is better. So, in an electrical circuit, the most important thing to remember is that the circuit transfers energy from one place to another. This is a model of a circuit that contains a cell and a lamp. The energy is coming from the cell and is being transferred to the lamp. Now, the first thing for you to do is to pause the video and have a think, by looking at the model, of what you think represents the cell, what represents the lamp, what represents the energy, and what represents the coulomb. A coulomb is a unit amount of charge. So it's, in the case of an electrical circuit with metal wires, a group of electrons, delocalized electrons because of the metallic bonding, would form a coulomb. Now, hopefully you've paused the video and you've had time to think about what all these things are represented by. Most of you will probably have worked out that the coal mine here represents the cell, that's where the energy is coming from, and that the fire down here represents the lamp, and that's where the energy is going to. And from that you might have worked out that the coal in these trucks represents the energy that's being transferred from the cell to the lamp. So the question is then, well, what are the trucks represented by? Because here we've got trucks that are full of energy, and here we've got trucks that are not full of energy, or coal in this case. And so what does the truck represent? And in this model, the truck represents a coulomb, so that is a unit amount of charge. So in this case, the charges are electrons moving within the metal wires. And so what we have here is the idea that coulombs, the electrons, are transferring energy from the cell to the lamp. Some other important things to note at this point: there are no gaps between the trucks in this model, so that means that all the trucks have to move around the circuit at the same speed, because there are no gaps. They can't catch up or overtake any trucks, they can't slow down, they just all go round the circuit at the same speed. Okay. The other thing is that the trucks don't stop moving just because the coal has been given to the fire. The trucks carry on moving back up to the cell to get some more coal. And we're going to look at what these aspects of the model represent in an electrical circuit on the next slide. So the next thing to think about when we're considering this circuit is how does current and voltage link into this model of the circuit? And this is where this model becomes really useful. So we have two different figures here doing different things. So here you've got a little man with a clipboard, you've got another little man with a clipboard here, and you've got two men here with some probes. And this man represents an ammeter, and this man represents an ammeter, and these chaps represent a voltmeter. So this man with the clipboard is counting how many trucks go past per second. That's his job. And this man over here is counting exactly the same thing. How many trucks go past per second? And in an electrical circuit, this is a measure of the current, because the current is a measure of how many coulombs pass a certain point per second. Now, what's really important to note here is it doesn't matter where we put this man and his clipboard in the circuit. He could be here, he could be here, but he's going to measure the same number of trucks going past per second wherever he is in the circuit. And that's the same with current. Wherever we put the ammeter in the circuit, we get the same reading because all the trucks are next to each other, they all travel at the same speed. So everywhere in the circuit, you're going to have the same current. Now, it's also important to note that these ammeters have no interest in how much coal is in the truck. They don't mind if these coal trucks are full, and they don't mind if these coal trucks are empty. They just want to know how many trucks are going past per second. These guys down here, on the other hand, that make the voltmeter, they're interested in something very different. They want to know what the difference is, what the change in the amount of coal per truck is. So this guy here, he measures how much coal is in this truck, and this guy here measures how much coal is in this truck, and they compare their answer and they get the change in the coal per truck. And this equates to voltage, because voltage is the potential difference, so the difference in the energy per coulomb. And you can see that because we've said that coal is energy and that coulombs are truck, that's the coal per truck. So they're measuring how much energy per coulomb has been used up by this lamp here. They're not interested in how quickly the trucks are going, they're just measuring the change in the energy per truck, or the change in the energy per coulomb. So current is the number of coulombs passing per second, and voltage is the change in energy per coulomb. So here we have our definitions and our equations for current and voltage. So current is the rate of flow of charge. The symbol for current is I, and current is measured in amps, and the symbol for amps as a unit is a capital A. And you can see here we've got our equation that current equals charge over time, so the rate of flow of charge. For voltage, we can use the term voltage or potential difference. The examiner doesn't mind which one we use. The examiner is going to use the term potential difference in the exam paper. So the definition for that is the work done, which we know from our previous work is the same as the energy. The work done per coulomb by a component in the circuit. The symbol for voltage is V, and it's measured in the units, volts, and the symbol for volts is V as well. And we have our equation here, voltage equals energy over coulombs. So the energy per coulomb. So now we need to have a little think about series and parallel circuits. So here we've got the coal model, but for a series circuit. You can see that we've got two lamps in series. And we need to think about what happens to the current and what happens to the voltage. So the coal is put into the trucks by the coal mine, and the trucks move around. All the trucks are bumper to bumper, so they move at a constant speed. They're all moving at the same speed. So these little men here, who are the ammeters, they're counting the number of trucks per second, but you can see all the trucks are in one long loop next to each other, so they all move at the same speed. This means that the current in a series circuit is the same everywhere in the circuit. However, if we have a look at the voltage, we can see that the voltage here in the cell, you can see that we've got an empty truck and a full truck. So there's a big difference in the energy per coulomb across the cell. But if you compare that difference to down here, here we've gone from a full truck to a half empty truck, and here we've gone from a half empty truck to a completely empty truck. So the potential difference here from going from empty to full, so that voltage, that change in the energy per coulomb, is equal to the change in energy per coulomb across both of these components here. So the voltage across the cell is shared between the components in series. So in a series circuit, the voltage across all of the components is the same as the voltage across the cell. So to summarise, here are our series current rules. The same current passes through each component. The total potential difference of the supply is shared by the components. And the total resistance, which we're going to talk about a bit more in a minute, is the sum of each component. For cells in series, if cells act in the same direction, as in here, so you can see we've got positive, negative, then the potential difference of the cells in series is the sum of the potential difference of each cell. So if this was a 3-volt cell and a 3-volt cell, we'd have 6 volts here. However, if they don't act in the same direction, that is not the case. So now we need to have a little think about parallel circuits, and you've got the Cole model here for a parallel circuit. You can see we've got an ammeter here, an ammeter here, and an ammeter here. And we've got voltmeters here and here. We've got 2 lamps in parallel and our cell at the top. And what we have here and here is a junction where the circuit flows, and then there's a junction, and it could either go down this branch of the circuit or down this branch of the circuit here. And this means that the current and voltage rules are different in a parallel circuit to in a series circuit. So first of all, we're going to look at the voltage in this parallel circuit. You can see that across the cell we've gone from an empty truck to a full truck. So the change in energy per coulomb is big. Now the trucks are going to travel along here, and then at this point here, at the junction, the trucks can't split in half. So one truck will go one way and another truck will go the other way. But that doesn't affect how much energy is in each truck. So you can see here we're going from a full truck to an empty truck, and here we're going from a full truck to an empty truck. And that means that in a parallel circuit, the voltage across the cell is the same as the voltage across the components in each branch. But if we now look at the current, that's a different matter in a parallel circuit. So as we said, the trucks travel along here, they get to the junction, and then some trucks will go one way and some trucks will go the other way. And then they meet back at this junction here, and then they all go back round through the cell. Now what this means is that there are more trucks passing per second in this section of the circuit and this section of the circuit than there are in here and here. So we're going to have a faster current here, and a faster current here, and a slower current here, and a slower current here. Now if we label the trucks, this can help us see what's going on. So here I've got trucks A and B alternately coming out of the cell, and then they get to the junction and all the A trucks go this way and all the B trucks go this way. And then when they come back round to this junction, they then merge back together, so you've got AB, AB, AB. Now, if I've got a current here of, let's say, 1 amp, which would be 1 coulomb per second, and if I've got a current here of 1 coulomb per second, then it makes sense that when those two join together at this junction, here I'll have a current of 2 coulombs per second, so 2 amps. So in a parallel circuit, the total current flowing into and out of the cell is split between the different branches. So in a parallel circuit, the potential difference across each component is the same, and the total current through the whole circuit is the sum of the currents through each of the separate components. So we've talked about current and voltage in series and parallel circuits, but now we need to talk about resistance. What is resistance? So resistance, a component with a resistance of 1 ohm will convert 1 joule of energy per coulomb with a current of 1 amp. Its symbol is R, and it's measured in the units ohms. And here is your equation here. So we can calculate the resistance of a component by measuring the voltage across a component and the current flowing through a component, and dividing the voltage by the current. This definition, although very thorough, it's a little bit difficult to understand. So it might be easier to think about resistance as a measure of how hard it is for the current to flow in a circuit. If you have a component with a higher resistance, it's harder for the current to flow through that component. Resistance is a property of the component, so you could have a lamp with a certain resistance or a motor with a certain resistance. And we can work out the total resistance in a series circuit by adding the resistances of the two components in series. So the next question is, how do voltage and current and resistance all interact with each other within a circuit? The voltage will affect the current and the resistance will affect the current. So if I increase the voltage, of the cell in the circuit, I increase the current that flows. So I'd increase the number of coulombs that pass a point in a second. And if I decrease the voltage, I decrease the current. However, if I change the resistance of the components, so if I make the resistance bigger of a component and make it harder for the current to flow, the current will then decrease. So when you're looking at a circuit problem, you need to have a think about the voltage and the resistance and the impact they have on the current. Now here we've got a summary of all the different quantities we're going to see in the electricity topic. The symbol that's used to represent them in equations, which is here, the units that they're measured in, and the symbols for those units, and then the definition here. Because we're looking at so many new quantities, it's worth making sure that you are familiar with this table and that you're confident and happy. You might want to make your own version of this table, but you must learn the symbol of each quantity and what they measured in. And be really careful because, for example, here, work done, the symbol for work done is a W, but the unit of power is watts, and that's a W. And it can get quite confusing. Some people get confused about the I being the symbol for the current. So, if we're concluding off everything that we've looked at today, the current in a circuit is given by the equation I equals Q over T. So that's the current is equal to the rate of flow of charge. It's the same everywhere in a series circuit. And the sum of the current in the branches for a parallel circuit is equal to the total current flowing through the cell. It's the rate of flow of charge in a circuit. The voltage is given by the equation V equals E over Q. So voltage is equal to the change in energy per coulomb. In a series circuit, the voltage is split across the components in the series circuit, but in a parallel circuit, it's the same across each branch of the parallel circuit. And the voltage is the change in energy per coulomb. So hopefully that's been helpful. Make sure you've got notes down in your exercise book and you've got a list of questions. There should be a lot of questions on this topic, and bring those to the next lesson. And remember to go back and re-watch certain aspects to help them make more sense.